out speakers, good. Hello everyone. This is a introductory talk to streams, but it also includes some of my experiences building a program in my spare time with streams. And I must say thank you to my new employer, Digital Asset, for letting me come here today and talk about this. And we're also hiring, so please do come and talk to me if you're interested in applying Haskell to blockchains. Although we don't use that word. Right. We are distributed ledger technology. So I thought I'd start off with what is a stream. And my own definition that I came up with was a potentially infinite sequence of data elements processed incrementally rather than as a whole. It's also an abstraction that offers an alternative to mutable state, although that's a talk in itself. But I often think functional programmers like to think in terms of streams. You know, an object-oriented programmer may think of modeling a bank account with an object, and they'll think of just mutating that object state for the latest balance. Whereas I tend to think of a bank account as a stream of transactions, and with indexed by time. But also streaming, of course, captures perfectly, I think, our interaction with the outside world. And also, of course, we like them in functional programming because we can program with pure functions and immutable values, and because we're in a pure functional language, we can therefore compose stream functions, and we can reason about them in isolation and compose them safely. You know, when you have mutable state, you cannot really compose things safely. You know, objects don't compose. So here's a simple backup program that I wrote, and it's okay. It does the job. I mean, obviously there are lots of issues with it, but it fits on one slide. But it is, of course, monolithic. I mean, it'll work no matter how much data we have on the disk, but it's monolithic. So can we make it modular? We need to break it up into composable, reusable pieces. And of course, you know, as we all know, I don't have to tell you all this, but we should end up with code that's easier to reason about, modify, and extend. So here is a piece of it that I've pulled out, and it has a particularly big issue, and I'm guessing you can all guess what that is. And you can actually tell it from the type. You can, I think I've got a laser thing. No, wrong button. Okay. I shouldn't press buttons, I don't know what they do. Okay, I thought I had a laser on this. So, yes, you can tell from the type that it's IO list of file path, which is telling us that when we use this function and we sequence it, we're going to get a list of all the file paths, and of course that list is unbounded because this is recursively exploring all the directories. Perhaps it should have recurse in the name, or recursively in a name. That list is going to be unbounded, and you run it on my hard disk, and it's going to blow the heap. So yes, monadic I/O is strict, and sequencing an action of e.g. I/O list of A will fully evaluate the entire output list in memory. So in fact, we should always be wary when we see that type, I/O list of A, that we may run into problems. It's really a bit of a code smell if you see I/O list of A. And so many functions in our Prelude return that. I mean, mapm is of course one. So if we want to be able to write efficient, bounded space, effectful programs, we have to ignore types like that. So one thing we could do is parameterize with a callback, and this is very popular. To use callbacks is very popular. And here we can just pass in something to do, and of course this will get suspended. The computation inside enumdir will get suspended whilst we run this callback, and then the computation will resume after we've run it. And this is how you would use it. You get sort of nested code like this. But I argue that programs soon become difficult to reason about at scale when you use this. I mean, they call it there's a name for it, callback hell. And really there was a senior chap at my former employer said that he didn't like functional programming because he liked to think in a linear way, do this and do that and do this. And really, actually, because of the expressive power of functional programming, we can actually turn a lot of problems into a linear do this and do that. I mean, asynchronous programming is one such thing where actually in the functional programming, we can write it in a linear workflow, and the less expressive languages, they do have callback hell. So I think, this is used commonly, but it's not what we're going to do. In effect, we're going to try to generalize this pattern of suspending the computation and then continuing. Can we use lazy evaluation? Because of course, in the seminal paper "Why Functional Programming Matters," John Hughes talked about lazy evaluation allowing these sort of modular pipelines. But it applies only to pure pipeline compositions. And for that, it works. So for example, you can write mapf.mapg, and you get similar efficiency to mapf.g. But it does have unpredictable space use. So if you have a function, for example, that takes a list of A and a list of B, and returns a list of B, just like mapf, and you have a function that takes a list of B, goes to a list of C, it's very difficult to know, in general, if g.f is going to work as nicely as mapf.mapg did. Is that space efficient? In practice, the consumption pattern has to match the production pattern, and it's hard to get right. And of course, it does not work well when made to mix with effects. How do I know that? Well, I know that because of the lazy I/O abomination. At best, it's a hack, I think, but I really don't like lazy I/O. I think it's I think it's a mistake. It was a mistake to add it. I guess historically they thought it was easy. They thought it was easy to justify based on the fact that in Haskell every value has bottom as a potential. Every type, sorry, has bottom as a potential value. So every A you've got here, could blow up at runtime because of partiality. So perhaps that was part of the justification. Lazy I/O is enabled by this primitive here, which well, I'll read it out. But when passed the value of type IOA, the I/O we performed only when the value of A is demanded. So if you like, the I/O here has been pushed inside the value A. It is there. But of course, it's highly this means that evaluating pure functions could trigger I/O. It's no longer clear where exceptions will be thrown or when file handles will be released. We tell beginners that here with hgetContents that the effect happens and contents now has the value string. But if I close the handle and then try to print the string, I don't get the string. So you can no longer use the type with lazy I/O. You can no longer reason about what's happening with the types. So I think it's I think this is one of Haskell's warts. But people are now moving away from it, which is good. So can we add streaming to monadic I/O in a safe and principled fashion? And I think that the simplest example of this, I think, is the so-called list T done right. And this is the name that the community has given to this pattern. And it's very simple because we basically start with a simple Haskell list. But we deliver the we have a monadic action here. That in many cases will be I/O that you have to run, and when you run it, it'll yield a value, A, and it'll also give you the rest of the computation, if you like, the suspended computation. So this is often called a generator. You're running some code, it's running, it then yields you a value A, and then the rest of the computation, and then it's up to you to then continue the computation. But this is very easy to understand, I think, because it's just like a linked list, except that we have this we have this M here, which is obviously inside here as well. And I've derived a functor for it. It's a functor in A here, in here. So if we were to F map over it, then we can change all these A's to something else. And you can actually define a lot of the sort of prelude list operations on it fairly routinely. I mean, this is boilerplate code. I won't talk too much about it, but you can hear that. You can hear I'm defining a monoid inductively. The only complication is that I have to get the underlying monad M here, which, you know, as I said, in many cases is I/O, and I have to then sequence it to get the result out that is either yielding an A and a suspended computation, or the tail of the stream, or a nil. And then once I've done that, I can then just recursively call mappend again. So these are very similar to the vanilla list definitions. And the monad instance is, I mean, this lets you use do notation, which is useful because then you can lift things, lift other actions into it. But essentially, though, it's just concat map. So it's very similar to the list comprehensions. And these monad trans lets me lift an arbitrary action. And when I run this action here, when I sequence it, I get a value out from that arbitrary action that I've lifted, and I can pop that value. I can make a singleton list with that value in it, and that lets all of this machinery means that actually, there's one more slide. There, after we would use return obviously to yield a result. You can see that from the previous slide here. I can take an X and I can construct a con cell with that X in and an empty tail for the stream. So I can use the return to yield a result, yield control, and then I would use something like this to eliminate the stream. This is map m underscore, and that takes you from a list TMA to just the underlying monad. So if it's I/O, then it would take it to I/O unit. So this is what I would use to eliminate my stream. And if we as I said, M is mostly I/O, so I could put I/O in there and call this, I don't know, stream prime A. And this would be very similar in expressiveness to the iterable in Java or the IEnumerable in C#. Very similar in expressiveness. Of course, those interfaces are very deeply baked in to C# and Java. They're in fact baked into the language because they have this for each syntax that relies on them. So it's very difficult for them to go beyond this. So we will go beyond it though. Oh, and here's a little example. So here I'm return 1, return 2, return 3. It's a very trivial example, but you can imagine I don't have to just return 1. I can do some I/O and get 1. And then here I've used the list monoid instance to join them all up. And if you instantiate with the identity monad, there's a nice toString, so you can see what it would look like. And it's essentially a linked list when it's instantiated with identity. And I can write the pipeline composition now. I've got my enumdir. I'll show you the implementations of these. I've got my enumdir, I've got my copy files, and I've got a pipeline. And this pipeline is, okay, the dot operator means you have to read it backwards, but it's still a linear pipeline. Do this, do that, and then do this. And these are the implementations of those. Enumdir is exactly the same as the one that we saw earlier that had memory issues. It's exactly the same. Only the type has changed. It's now stream prime file path, and this bit here is this line is slightly different. But otherwise, the code is the same. So this is a very easy change to go from to go to a streaming version of this. The copy files is the function that consumes the stream. So that copy files is eliminating the stream, and it contains some code that again is taken from that monolithic first program that I showed you. So what are the problems then with this? Because it seems like a very good abstraction. As I said, it's very similar to iterables in Java. What's the problem with it? Well, there's no final return value. It just returns nil. At the end of the list, you just get nil. And this actually makes it impossible to implement fully streaming versions of many common list operations. And split-at is an example that the streaming library gives on the streaming library that I will be talking about gives. And it's also we've hard-coded a functor, this sort of partially applied pair here. We've hard-coded that in the cons cell that we had. We've hard-coded that functor there, and that also prevents things that we could do. For example, we can't really correctly implement a stream of streams, which we would need for chunks of. So you can imagine chunks of gives you streaming chunks. So there are some problems with this. So this is a better stream type. And it turns out actually that there's actually less code than the other one because we've parameterized things. So there's actually less code than the other one. So here we have, I've called this one stream. And we have, rather than the cons cell, I've called this wrap now, rather than the cons cell, we now just have a functor f. And so you can imagine a very instantiating it with the functor we had earlier, the partially applied pair, and then so this would be the tail, and then we'd have an a here as the head. And this is the other big difference, that here we've got an r. We've got a parameter for a return value. Now it turns out this is a free monad transformer. So so this has a name in mathematics, which tells me that it's not ad hoc. It's not an ad hoc abstraction. And here is a slightly more convenient functor that I'm going to use. There should be a deriving functor there. This is less strict, so it will evaluate the a. That's just a nice infix data constructor. Yeah, it's an infix data constructor. So rather than it just looks nice. Yeah. And then the yield, we have a yield primitive to yield a value, and this will take a value a, call this wrap, and it will use this functor here. So this yield is tied to this particular functor. It is tied to the of A here. And then we want a monadic bind, but this one is different to the other one we had. This one is not like a list comprehension. This is really like concatenation, because here we're getting the if you imagine we're doing the bind here, the R we get there is not every list element of S, but this R is the return value of that stream. That stream has a return value, and so we're not getting every value from that stream there, and then doing a concat map. We're getting the return value of the computation that represents that stream, and that stream is still yielding values that are being consumed, but bind is working very differently. In fact, it's simpler than the other one. It's a simpler bind. It just will concatenate the streams. MapM looks similar to the previous one. So here's the nice infix data constructor there. Yeah, so this looks very similar. Here we're eliminating the stream, and we're ignoring the return value here. And then, yeah, so I don't need the monoid instance. I can just sequence these yields, and I get a similar answer to the previous case. Now, it turns out that this has already been done very nicely. There's a package called streaming. It's very well done. There's a nice comprehensive prelude. The authors have thought a lot about the efficiency of it. That's why it looks a little bit different to my one. It's been designed in such a way that GHC will optimize it efficiently. But it's essentially it's isomorphic to what I just showed you. It is essentially the same. And they do have implementations of split at and chunks of, and you can see that the split at utilizes the return type at the end. So you have a stream of A that returns a stream of A, and you have a chunks of, and this changes the functor here. The chunks of gives you a stream of streams that is streaming. So then. I was very impressed with this library because I thought my only criticism was that it was 10 years late. but I was very impressed with this library, and I sat down on my train journey because I get a seat, and I tried to implement something substantial with it, and I wrote a backup program that's got quite a lot of features in terms of it duplicates. It does content-derived chunking to split up your files according to boundaries that won't move if you append bytes to the beginning of files and so on. And it will upload all those things to a content addressable store in the cloud. And it's all been built using a streaming library, and it's very fast. It can go through and work through the Linux kernel in less than 30 seconds, and then subsequent incremental backups take about a second. So it is very fast. I might be able to show you a brief amount of the code if I try to. Flick to an Emacs buffer. So there's a file called pipelines, which has the main top-level pipelines, and you can see that it's written as these pipelines that I will recurse directories. I will filter out items that are relevant to me, and then there's a streaming diff here, because often if we're doing an incremental backup will have to, there's a diff that's naturally involved, and there's serialization, and there's upload pipelines, and verify pipelines, restore pipelines. One thing I did notice when I looked at some guys that had written similar program in Go is that they had implemented diff quite a few times throughout the code base. So there were at least 3 different places where there was a diff. Whereas because I've abstracted diff, I use that a few different times in the code base. There's one place where you diff the snapshots, diff the files in the snapshots, and here when it's working out what files have changed, and so on. So yes, these files are all. If I go to commands, there's a file called commands where all the command line arguments map to functions in this file. So every run command function in this file basically invokes a top-level pipeline and then runs the stream. So you can think of the project as being commands that invoke top-level pipelines, and then there's a file with all the top-level pipelines in, and then there are many other files with smaller pieces that get reassembled. So let's, and it's on GitHub. It's a new project, and contributions are welcome. Now let's go back to the talk. I'm not sure what the shortcut is to do this. Presentation mode. Yeah, it's GNOME software, so they don't believe in shortcuts. Presentation, right. Yeah, so my tips, the tips I can offer after building this is that streaming is a good fit for the large-scale architecture of an application. So in this Atavachron backup, I'm typically streaming chunks of bytes. But it is not good for fine grains of performance-critical sections. I've seen on the web people trying to do Monte Carlo simulation with streams and things like that, and that just to me feels wrong. Stream word 8 is not going to perform well. It's much better to, and GHC Haskell has the facility to work with arrays and very well, and there's ST monads and things like that. So if you're working inside a chunk doing content-derived chunking, then I'll use arrays, and I get very good performance. And then once I have a chunk, and in terms of the larger architecture of the application, then it streams. I've got parallelism in this as well, and I found that that I had to often sacrifice ordering of either the elements or of the effects. What I chose to do is I chose to forgo the ordering of the effects. So I had an evaluate that would, if you like, evaluate a whole load of effects up front to get me to fill a buffer of elements, and then that buffer of elements I could do in parallel. But in order to do that, I had to, if you like, force a load of the effects to happen out of order with the elements. That was safe for me to do, but you have to, when you build your own applications, you have to think about whether that is safe to actually do. So sometimes you have to, you have to forgo ordering often, it turns out that for me, I could forgo the ordering of the effects relative to the elements. Other cases in the code base, I had to forgo the ordering of the elements, but that was okay because I could actually recover that. Just needed a bit of additional space and time to do that. I did also think about synchronous streams. So in this program, there are chunks that, and there are also files. You can have a stream of files, but a stream of files may lead to many chunks. A file may lead to many chunks, or actually one chunk may contain many files. So it was difficult in this program to have the idea of a synchronous stream where there is a clock if you like, a clock signal. It wasn't clear to me what that would be. So I didn't go with synchronous streams, but other applications may benefit from that. And what that means is if everything has a tick or a pulse, it means that suddenly you can do circuits and arrow combinators and fancy things like that. And yes, there are, but that's an area that I didn't explore. And also automatic releasing of file handles and other resources. I use the resource T, which worked out of the box for me. It's just a monad transformer that I layered on top of my streams, and it meant that the file handles would get closed and so on. However, it should be said that the prompt finalization does remain an issue with this streaming library. It turned out that for me, things worked okay, but you have to understand that it won't necessarily release the file handles straight away. So where can we go for more advanced libraries? Well, I think it's fair to say that the state of the art is embodied in the iterate library. This has confusing names. When I learned it, I found it very confusing, and I think it's because it comes from a sort of a parsing logic world as opposed to a streaming world. We like names like, when we talk about streaming, we like names like producers and consumers and sinks and sources, and so it's definitely been a hard one for many people to grasp. But I think the biggest difference between the iterate library and what I showed you is that it has this two-way communication. So I think it's correct if I say that they're, rather than having generators, they're more coroutines. They can take arguments. These suspended computations can take arguments, and that gives them this two-way communication. And then with that two-way communication, they implement all these features like prompt finalization is one of them, so and they offer back pressure libraries for buffering and things like that. And there are some attempts at concurrency as well. My colleague at Digital Asset, Ben Lippmeyer, has done a nice library for concurrency and streams. But pipes and conduits, which are the two most popular variations of this idea, they're very similar to iterate, so they're based on that idea. I think it's fair to say. What they do though is they provide lots of abstract APIs which help ensure that these streams are used correctly, because what we need is linearity. Of course, we can't duplicate streams necessarily safely. We can't discard these suspended computations and so on. So the approach that pipes and conduits have used are to sort of put APIs on top of those data types that I showed you to try and enforce safe usage. But I think it's fair to say that in the future, when linear types gets more, when that arrives in GHC, it'll open a lot of opportunities for simpler streaming libraries that are safe to use. And there's a paper called on the duality of streams, which talks about that. So my summary is that streaming is a fundamental abstraction and key to building many real-world applications. But I also think there's no one-size-fits-all streaming library. They all have a trade-off between ease of use and features. So I think we just need a good interoperability story. We need to easily, if one project's using pipes and others using conduit and others using streaming, we just need to easily be able to convert between them. I also think understanding list T and stream, as I've showed you, is the basis for understanding all approaches. The idea of suspending a computation, delivering a result, and then abstracting over that is key to all the approaches. And also, as I said, I'm a big fan of this streaming HaskellX package. It strikes a good balance between simplicity and practicality, and I have used it to build something in my spare time with great success. That's doing non-trivial code, and that's all I had prepared. Any questions?
Can you just say something about the prompt finalization thing?
Sure. So if you imagine we've got a file, and we've opened that file, and we're now streaming the contents of it. And let's say we have a combinator that gives us the lines from that file as well. So we've opened the file, we're streaming the contents, and we've got another combinator that's splitting the file up into lines. And let's say we just want the top 5 lines. We say take 5. What we might want to happen, and perhaps let's say we're doing that for many files. So we're saying take 5 of this file, take 5 of that file, and take 5 of the next file, and we've got an outer do, and we're doing that. We want those files to be closed as soon as we've done the take 5, and we're moving on to the next file. But actually you need sort of prompt finalization for that to happen, because you downstream it doesn't know you're only interested in the first 5 without some sort of two-way communication. It's very and so what will happen is that typically the file handles will get closed when the outer computation finishes. So it's it is an issue, but it hasn't bit me. If it bit me, I'd have used pipes or conduit. But it seemed fine to the streaming library worked fine for me. I think that's because I was basically draining the files of their content, so it was clear. It was clear when to close the file and then move on to the next one. Yes.
What were the reasons why you choose streaming instead of conduit and pipes? Just personal preference or any fact-based?
It was really because it was such a simple library and simple and elegant library, and it seemed to me that given how far the Java and C# programmers get with their abstractions, that it seemed to me worth a shot at trying, seeing if the simple library worked for my needs before moving on to the more complicated one. So it really is very easy to use, because most of the time, as you might have seen from the screenshots of the program, it's mostly just function composition, and so it definitely seemed like the thing to try first because it was the simplest. And then I see conduit and pipes as being something that if you don't know what your requirements, if you don't foresee that you'll need that two-way communication, prompt finalization, those sorts of things, if you don't foresee it, then you should probably try to use the easier library first, the simplest library first.
A second question. You spoke of parallelizing your problems. Did you run in any problems with the prompt finalizations in there?
No, I didn't know, because likely laptop only has 4 cores. I would have just maybe I had yeah, 4 times 4 on the number of file handles open or something. So yeah, because I'm basically reading the files off the disk one at a time, so it was fine. Actually, it may be worth showing you just for interest. What's wrong? I need to escape. Sorry. If I go to just for interest, I had a few. This is my file of things in here that I use. I wrote a very simple par map, which uses this function here, which evaluates the stream ahead, forces the effect ahead by n items. So I had a very simple par map where I create a load of async tasks. I map over the stream to create some async tasks. Then I force the effects by a certain number of items, and then I map weight. So it's almost a bit like a sort of sliding buffer, and this was enough for me. So the great thing about this par map is it maintains element ordering. What it sacrifices is effect ordering relative to the elements. So that's how I did the parallelism. No, it's not. It's in my I'm too much of a perfectionist to contribute anything upstream. Yeah. There's a few other things that I wrote as well. I don't know, there was missing sort of obvious list functions like map a queume. I added those, but they're quite simple to write. There's one very dangerous one. Where was it? Yeah, this one's. So this one maps over left values, leaving the right values unchanged. So you have a stream of either. This one, if you don't have synchronous streams, you see, you need to know what you're doing because what I do here is that when I provide a function that I map over the left values, the bits I'm skipping, if you like, end up as the effect. So it's using this parameterized functor. It's a tricky bit of code, and it doesn't work. It doesn't work very well with that. You need to know what you're doing if you haven't got synchronous streams. You know, it doesn't obey the arrow laws, but I still found it useful. So there are all sorts of fun things that you can do with this parameterized functor, and I used it to implement the sort of arrow left.
You mentioned that there was a tension between coarse-grained and small-grained.
Yes.
And you said that streaming was for coarse-grained stuff, and you would discourage for fine-grained stuff.
I think so. Yes.
Right.
Yes.
But to me, that's a bit of a shame, right? Because some algorithms really are, essentially processing things sequentially. And you're saying if you're using that, if you're doing things, say, word by word, you're going to be paying a performance penalty if you're using the streaming library. How do you think that this is something that could be solved one day? I mean, presumably the compiler could realize this, could do some chunking, for example. Perhaps could you build a library where you're still expressing things not in terms of chunk at a high level? You're writing things, saying, I'm writing things modulo chunking.
Yeah.
But then at the top level of your program, you're giving some kind of chunking parameter.
Yes. No. It's possible. I mean, the chunking happens everywhere, and it's even in things like data dot or lazy byte string, for example. You know, is effectively there are chunks of arrays. So streaming, I guess you could try to have an interface that looked as if it was. I think your question is, can you have an interface that looks as if it's working with single elements, but under the bonnet is maybe chunking?
Yeah.
Yeah.
Streaming by string library for this.
Yes. Yes. There is a streaming byte string library. Yes. There is. They've redone byte string on top of streaming. Yes. So yeah. So that would be. That's fine. I think that's fine. It's just when you've you know you really do have a. If you really are yielding a word 8 at a time, that's likely to lead to performance issues.
Right. Although there's fusion that should eliminate some of that.
Yes. Yeah. That's yeah. If the fusion, yeah, then you can end up with very brittle code and that needs the fusion to fire and yeah, it's yeah, I think there's work to be done in that area, but perhaps that's the best way to explain it. There's some work to be done in that area. I mean, for me, I just when I came to that level of granularity, I just used arrays directly, and then just used the streaming for the large scale stuff. But this, by the way, is available on GitHub if anybody's interested. And actually the slides for the talk are will be on the web at some point as well.
I have another question. So in the free T effect constructor, what would happen if there were a bang in front, reinforced evaluation or ask evaluation district there?
I'll have to go back. Let me go back. So we have this one here. So where is the bang?
No, sorry, the stream the transformer version. Yeah, this one.
Oh, why have they put a bang here? Well, I guess this functor is typically not a computation. It's typically a data. You know, yes, it's typically a value. So they just want to be strict there, so that it's when step is constructed that value is constructed. It's generally a good idea in production Haskell actually to have strict data, and I think there's even an extension to turn it on automatically. Thank you all very much. Thank you.